There, now the audio's on. Okay. Yeah, what does this code do? Take a moment, look at it. I'll give you a minute, look at it, what's it do? There is no magic trick going on. There's no new rule you need to be aware of. Just follow the rules you've been taught since week 2, whenever we started talking about functions. Just put your hand down. We'll just give everyone a chance to think about it, look at it, see if you can decode what's going on. You have a question or an answer?
I think I have an answer.
All right, I'll wait a second. I'm going to give people just one more chance. And when in doubt, follow the code. What does the code say? Execute it on paper or in your head, whatever. All right, raise your hand real high if you have an idea. Really high, I want to see. Okay, you've got an idea, cool. So, let's think about it. Let's just do an example. I'm gonna, instead of saying fact every time, I'm just gonna write F because I'm lazy. So, we'll just execute this code on the whiteboard here. So if we have F of n, well, let's say F is 5. Can you see that reasonably well at the back there? Yeah. So what does the code say for us to do here? Well, is n, which is 5, equal to 1?
No.
No. False, whatever. So we don't have to do that. So we go to the next thing. So what we're going to do is we're going to return, this is equal to 5 times fact of n minus 1. Well, that's interesting. F of, well, what's n minus 1 here? 4. No big mystery there. Great. So in order to answer this question, the answer to this question is simple. The fact that f of 5 is just 5 times f of 4. That's it. That's all it is. But raise your hand if you're like, well, there's a bit of a catch there. Of course. Because in order to answer this question, what do I need? I need f of 4. I need to know what f of 4 is. All right. But it's fine because we're actually calling f of 4 on that line right there. We are saying, call the function fact with the value n minus 1. So what's fact? Well, I can draw it kind of like here, I guess. F of 4 equals 4 times f of 3 minus 1, because of course 4 is not equal to 1. And then f of 3 is equal to 3 times f of 2. We're running out of room here. We'll just draw it over here. F of 2 equals 2 times f of 1. So I don't have the answer yet. I'm kind of like taking steps down. I'm going lower and lower and lower. F of 5, well that's just 5 times f of 4, but what's f of 4? Well, it's f of 4. F of 4 is 4 times f of 3. What's f of 3? Well, that's 3 times f of 2. What's f of 2? And so on. We're just going to keep going on forever. But here we actually have a special case. N equals 1. What's the answer to fact 1? 1. There's no mystery there. If I put in 1 for n, the result's 1. Great. So if f of 1 is 1, I can now answer what f of 2 is. Because f of 2 is just Someone's playing a joke on us, I think.
Again, are you sure that's some whiteboard marker?
Yep.
Okay.
What's it say? Whiteboard marker. Lumo color, but they spelled color wrong.
How do they spell it?
Well, they missed the U.
That's the way I spell it.
That's American version British spelling.
Do you honestly think I don't know that?
That's the way I spell it.
So you spell it wrong. That's too bad. So, if I know f of 1, I could answer f of 2, which is simply 2 times f of 1, but f of 1 is 1. What's 2 times 1? 2. So f of 2 is therefore 2. So I can replace all of the f of 2 stuff here with just what f of 2 is equivalent to, which is, of course, 2. Therefore, f of 3 is now 3 times 2. Exactly. Which is 6. So this, of course, is 6. So we can replace all of the f of 3 with 6. So what's 6 times, or pardon me, f of 4 is now 4 times 6. 24. Great. So all this is 24, so I can replace all of this with what f of 4 is, which is 24. And then, of course, f of 5 would therefore be 120. Notice how, in order to answer what f of 5 is, I needed to have the answer of what f of 4 was first. And before I knew what the answer of f of 4 was, I needed to know the answer of f of 3, and so on. But it's kind of funny, because the way this is written, it kind of suggests like a really lazy way of evaluating it. If you call me and I'm a function, if I'm this function, and you say, hey, tell me what fact of 5 is, I'll be like, well, that's easy. It's just 5 times fact of 4. And then you're going to say, yeah, but what's fact of 4? I'm like, I don't know. It's not my problem. Although I'll call another function and have you tell me what fact of 4 is. And then you go, oh, that's just 4 times fact of 3. But what's fact of 3? I don't know. That's not your problem. But you can ask someone else to calculate that for you. And so on. Yeah.
So all this then essentially will do is it's just a guess, but it's just going to find the factorial of a number.
That is what this is calculating. And what's cool is like, well, factorial can be defined recursively. And this is a recursive algorithm. It's an algorithm that has like a definition of itself in the definition of itself. Fact of 5 depends on what fact of 4 is. It's something that's defined in terms of itself, which is weird, but it totally works. So let's take an example here. If I want to calculate how many people there's not enough people here to do this. I want to know how many people are in the last 2 rows in this lecture hall. So here's what I'm going to do. I'm going to ask you over there. Hello, you. How many people are there in the last 2 rows of this whole lecture hall? But you're not going to count them for me because you don't want to count it. Here's what you are going to do though. You're going to say, well, it's easy. It's me, 1, plus however many other people there are. But of course, it feels like, well, yeah, but you can't answer that question without answering the other part of that question of, well, how many other people are there? So that's kind of a bit of a problem, but that's okay. You're going to delegate that question to him. And you're going to say, oh, well, it's 1 plus however many other people there are. So let's do this. Let's execute this for a second. So I want to count the row of the last 2, the number of people in the last 2 rows, and in the middle we'll count the far back one as the 1, 2. So you 2 or you 3, you're not included today. I'm sorry. So How many people are there in the last two rows? Start with you. What do you say? Well, no. What I want you to do, maybe I'll be a little clearer. It's going to be 1 plus however many other people there are, but you're not going to ask that question. You're going to ask him to ask that question. So it's 1 plus however many people are left. So you tell me how many people are left. Well, it's 1 plus however many people are left there. But you're not going to answer that question. You're going to ask him. So how many people are left?
1 plus 1 plus 1 plus 1.
No, is the pattern not clear? You say 1 plus however many people are left. But you're not going to answer that question. All you're doing is the 1. So, let's try again.
1 plus how many people are left?
So you're not going to answer that question, but you're going to ask someone else to. Who are you going to ask? Your turn.
1 plus how many people are?
So ask someone to calculate that. So you better ask someone to calculate that for you. No, I don't know what he said. Are you going to ask someone else to calculate that for you?
1 plus the rest of all of them.
Keep going. Sure. Well, I want you to ask like the next person. You also skipped him, but. All right, we'll cut there and go back to you because we skipped you. So you go now. All right, figure out how many people are left. Okay, he's asking you. This really is supposed to be an easy exercise here. This is the hardest thing. Okay. Well, you keep forgetting the important part. You have to ask someone else to calculate that for you.
1 plus however many people are remaining. 1 plus however many people are remaining. However many people are remaining.
So how many people are remaining?
Probably overthinking it.
Yeah, you absolutely are overthinking it.
Look to your right. Is there anyone left?
So I can't hear you.
Well, there's somebody else on my right, so.
So how many people are left?
So.
Say the number. How many people are left, including you? Pardon?
0.
How many people left, including you? Say 1. All right, so now you can answer your question. Look alive, people, come on. He told you how many people are left. So what's your answer?
1 plus one more person, so 1 plus 1 in a sense.
So you are going to tell him, because he asked you a question, how many people are left, right? So now you have an answer to what your question was.
So it'd be 1 plus 2.
So you gave him 2, okay.
Then I'll say 1 plus 3.
No. All right. Are the people at the back just failing miserably, or am I doing a really poor job at explaining this?
I think it's a mix of both.
I've never had an issue before. This is the first year. You guys forgot how to count. Let's try again with you 5. It's going to be a much simpler example. Let's see if we can get it to work this time. How many people are there in this room?
1 plus
Or sorry, how many people are in that row right there?
1 plus however many people are in this room.
Not counting you, right?
Not counting
So how many people are left in that row?
1 plus however many are left. 1 plus however many are left. 1 plus how many are left.
And speak up loud. They can't hear you.
1.
1. Perfect, because there's no one else left. So you tell her.
1.
So how many are there?
1 plus how many other
Well, no. You asked him how many people are left. So you know that the total number of people left is his answer plus 1. So you tell her.
2, 4, 5.
Great. Much better. Still wasn't great. 4 out of 5. Because I'm delegating the question. The question was, how many people are left? Well, it's 1 plus, I don't know. You tell me how many people are left. And they figure that out for you. How they figure it out, I don't care. But they're going to get back to me. And once they do, I know that the total number of people in that row is what they say plus me, and I'm done. That is a recursive way of getting the answer. Or it was supposed to be, but it didn't turn out that way. And we can use this right here. So this is an example with fact 5. There's a cool little website here. And this right here is going to execute this code and kind of show us where it is in the code. So, next. So we run this function fact5. So n is 5. Is 5 equal to 1? No. Goes there. So now we have to answer what fact 4 is, though. It's not that. See how it's like working its way down until we get to that special case. We call this the base case. When we've got that like catch, like the bottom. So we've worked our way down to that base case. And then once we answer the question of that base case, watch what happens. So now it goes back up. Well, I went too quickly there. There you go. 120. Isn't that interesting? We have this function that's defined in terms of itself, which almost sounds like you shouldn't be allowed to do it, but because we've got that like special little like base case there, that end, that limit, that bottom, we're fine. So we go down to get the answer to the first question that has to be answered. Not the first question that was asked. The first question was asked was what's fact 5? But we couldn't answer that until we answered a series of other questions first. And we had to keep going down. Then we answered the first question that had to be answered, which was fact 1, which is 1. Fact 2 can now be answered, but it needs to be answered in order to know what fact 3 is, and so on. You had a question.
What would happen if we didn't have that base case?
What do you think? You tell me.
So, like, mathematically, shouldn't it be 0? You know, like, I mean, using that code, since we pass over 0, shouldn't the function return 0? But then it'll be going on forever, so.
It would go on forever if we didn't include the base case. Because it would say, well, what's fact of 5? Okay, what's fact of 4? What's fact of 3? What's fact of 2? What's fact of 1? What's fact of 0? What's fact of -1? What's fact of -2? And so on. It'll go on forever. You've created an infinite loop by doing that. It's similar to saying like while true, but you've done it with recursion instead. And it's interesting. There are some programming languages out there where there's no such thing as a for loop or a while loop. If you want to do anything with like looping, you got to use recursion. You have to do stuff like this, which is pretty cool. In fact, there was a year during my undergrad where all I did was program in like a language that did that. And then when I went back to Java, and then I like forgot how to do loops. I was like, wait, how do I? Because it takes a bit of a switch flip to go from loops to recursion. It's the same idea, but you kind of got to think about things a little bit of a different way. But I got so used to doing it the recursive way that it was hard for me to go back to loops. Going from loops to recursion is also fairly challenging as well, but it's not too bad. People always love to talk. Raise your hand if you've heard the word recursion before. Cool. So, raise your hand if you've heard like, oh, when you learn that topic in computer science, it's really hard, it's scary, it's big and scary. Well, that's good. Only 2 people. And you were lied to. It's not. It's one of those things that I think people like to talk about how hard it is. That doesn't mean it's trivial. It's not easy, but people talk about it as if it's a super hard thing. So students come in with this expectation of like, oh my gosh, I'm never going to get it. No. No. There's no magic trick here. What does the code say? Follow the code. Remember, that is the one silver bullet trick. What does the code say? Follow it. Don't make any assumptions. Just go. So recursion's pretty neat. Now, if talking about recursion, there's like, whenever you have a recursive function, typically we want two key components to it. Typically. We want our base case, kind of like the limit, the bottom, somewhere it's going to stop. And then we also need the recursive step, the part that calls itself. So if I go back up to this example here, this is the base case, this is the bottom, this is the recursive one. It might be easier to identify the recursive one first because it's the line that calls itself, like where it calls the function. And then the base case is the alternative. Those sorting algorithms we were looking at they're fine, but they're not particularly quick. There are other sorting algorithms that we're not really going to sink our teeth into. I'm only going to give you a high-level thought of how they work that use recursion that are a lot quicker. I mean, you don't have to do this with recursion, but it's easy to think about this recursively. So here's the idea. And we talked about this last week, I think. Here's what I'm going to do. I am going to take an unsorted list of things, all right? It's unsorted. I'm going to randomly pick one of the things in that list, randomly. Ideally, it's going to be one that has a value kind of in the middle of all of them, but, that's hard to find out without doing a whole bunch of linear searches, So I'm going to randomly pick one and just hope that it's going to roughly split the list. I randomly pick the number 72. So what I'm going to do is I'm going to go through the whole list and put all the numbers less than 72 over here, and all the numbers bigger than 72 over here. And then all I have to do is sort that list, and then put it all back together, and then I have a sorted list, right? That's it. That's all I have to do. But raise your hand if you're thinking, but wait a minute, you're skipping some steps. Of course I am. I said, okay, split it, and then sort that, and then sort that, and then once you're done, you put it back together, it's sorted. Because if I have a list that's sorted that are all numbers less than 72, a list of numbers that's sorted that's all bigger than 72, if I put it all back together, I have a list that's still sorted. Correct? Right? But raise your hand if you think if you can't help but think to yourself, yeah, but he's saying just sort that list and sort that list. But how the hell? You're skipping, you're not explaining how you're sorting that. Right? But it's the same idea as counting people in the row. I don't care. It's someone else's problem to sort that list. So imagine I take the smaller list. I'm just going to do that process again. I'm going to take that smaller list of all the numbers less than 72, randomly pick an element, and take all the elements that are less than that one. Maybe I pick 41. All the numbers less than 41 go over here. All the numbers bigger than 41 go over here. I'm going to sort that, and then put it all back together again when I'm done. But again, I'm saying split and sort, but I'm not explaining to you how to sort it. It's easy. Just do it again. Pick something, hopefully in the middle, randomly pick one, split all the things, sort, put it back together when they're done. But how do you sort them? Eventually, I'm going to keep going down and down and down and down and down. If I have a list of size n, and I get lucky and happen to split on a number that's right in the middle, how big will this list be and how big will this list be?
Equal.
To what value?
N divided by 2.
Thank you. Yes, n divided by 2. I'll have two lists of roughly n divided by 2 size. Then if I take this one and I split it, how big will it be? N divided by 4. I'll have two things that are n divided by 4. And then if I do it again, what will I have? And then if I do it again, what do I have? Divided by 10? Who said that? 16. If I keep going, what number is this approaching? What integer is this approaching?
1.
1 or 0, potentially. So if I keep dividing, and the lists get smaller, I keep halving them every time. They start at n, then it's n over 2, n over 2, n over 4, n over 4, n over 4, n over 4. It's going to keep going down until I have, let's say in a very ideal scenario, I have a bunch of lists of size 1. How many lists of size 1 should I have? I think someone said, I just didn't hear. N, exactly. So instead of one list of n things in it, I have n lists with one thing in it. But what's really neat about a list with one thing in it? It's sorted. Oh. So imagine I'm at that case where I have n is 2. And I split 2 over here and here. And I say sort it, sort it. Oh, so list of size 1, it's already sorted. I'm done. Just put it back together. Now I have a list of size 2 that's sorted. I'll have done that again over here. This list of size 2 is now sorted. This list of size 2 is now sorted. Put them together, now I have a list of size 4. So the trick here is I keep having the amount of work that needs to be done. And I know it sounds like I'm saying, yeah, and then sort the small size, or the smaller list. But if I keep doing that, eventually I'll get to lists of size 1 or 0 that'll be sorted, which is that base case in this scenario. So the basic idea here is I pivot on a number and put all the numbers less than over here, all the numbers bigger than over here. And I keep doing that over and over and over and over and over until I end up with a bunch of lists of size 1 or 0. Then I start putting them back together again. Then I start working my way back up to the top, that one list of size n, that will end up being sorted. Any questions about that one? So this sorting algorithm is better than the ones we saw before. The ones we saw before were always quadratic. They were always n squared, right? Sure, we had some of that best case scenario situations where it was linear, but for the most part, they're n squared. This isn't, though. This is a little different. Does anyone have any idea what this is? Not n squared. What is it? Any idea? Log n. So you're on the right track, but we're missing an important part. So every time I pick a pivot, I go through all the elements, all n of them, and put them on their correct side. Smaller, smaller, bigger, smaller, bigger, bigger, smaller, right?
Would it be log base 2 of them?
Well, log base 2n, yeah, log. When in computer science, almost always, if we say log, we always mean log base 2. So log base 2 of n, but that's not the answer to the question I'm asking here. If I have n elements, and I want to put all the ones that are bigger over here and all the ones that are smaller over here, how much work is that? N. There's n elements. I just go like, okay, you go there. I have to put my finger on each of them to decide which side they go on.
Log of n times n?
That's exactly it. We have to do n work some number of times. But tell me why it's log base 2.
Because after we do it, we take, when we sort the next half, we don't have sort with half of the other stuff. So everything's being divided by 2 constantly. I can't explain it. I
I know when and why, it's just hard to explain. in my-
Shouldn't be if you know why.
You know what, fair enough. Because it's being divided by 2, we have to, when we sort one of the lists, we stop ourselves from having to sort everything that was, with everything up that was bigger than X before.
Okay, I think you're on the right track. What were you gonna say?
I was just gonna say, is it base 2 because computers are all zeros and ones?
That's not why. It's a happy accident. It's base 2 because we are halving every time.
That was my 2% for the.
So the idea here is, what time is it? If I have n things, and I split it into 2 things of n over 2, then I split each of those things, n over 4, n over 4, n over 4, n over 4, and I keep going, then it'll be n over 8, 16, 32, 64, and so on. Eventually, I'll get down to n things that are size 1. 1, 1, 1, 1, 1, 1, 1, 1. Right? So, if I have n things and I need to put all the things less than and bigger than, how much work is it to do that? This was the easy question. N. So we've got n amount of work to do at this level of this tree thing. Then I go down to this level. How much work is it to do n over 2 stuff? N over 2, but I'm doing that twice. N. So on this level, it's n stuff. How about this? If I do 4 things that are n over 4, how much work is it? N. If I do 8 things that are n over 8, how much work is it? Exactly. I'm going to keep doing that. So for each level in this tree, we have to do n amount of work. So the question then comes up as, how many levels are there in this tree? Who's got a good guess?
Log base 2 of n.
Log base 2 of n. It's not n, it's because it's getting half as big every time. And eventually it's going to get to the bottom. So I need to do n work for each level. And how many levels are there? Well, again, don't worry, this is not on the test. This is not on the exam. It's to give you an idea of where things can go. Yeah?
Around what year would this stuff be taught?
This will be next semester. Yeah. But instead of getting 10 minutes of an explanation, you'll get much more. So that's one of those sorting algorithms that's quite a bit quicker than the quadratic one. Now here's another one. And this one is maybe a little easier to think about. I'm going to start with the basic, simple idea. Keep splitting the list into halves and halves and halves and halves and halves. Okay? But then, what I'm going to do is this fancy thing called merge. Okay? See if I can do it with this easier. Nope. What the heck? If I have the list 1, 4, 7, 9, no, let's do a 3, 4, 7, 8, 9. And I have the list 1, 1, 2, 5, 6. 8. Okay, I have 2 lists. They're both sorted. Ideally, these lists are the same size. They should be, in a very idealized scenario. So these lists are the same size. So here's what I'm going to do. I'm going to start at this number and this number. And I'm going to merge these lists. So one observation to make here is both of those lists are sorted, right? And this merge strategy I'm going to show you will guarantee that we merge those two lists into a bigger sorted list. The algorithm for merging is very simple. You look at those two numbers. Which one's bigger, 1 or 3? 3. Let me ask that again. Which one's smaller, 1 or 3? 1. Great, okay. So 1 gets put in. Then we're done with the 1. Now we're at this number. And I ask the question, what's smaller, 1 or 3? Okay, great, 1. So we merge that number and we move on to the next one. What's smaller, 2 or 3? 2. Great. What's smaller, 3 or 5?
3.
Okay, 3. What's smaller, 4 or 5?
4.
What's smaller, 7 or 5?
5.
What's smaller, 7 or 8? Yeah, 7. Then what's smaller, 8 or 8? Doesn't matter. We'll pick one. Let's say we went with the top one just because. What's smaller, 8 or 9? 8. Okay, we're done this list. Now, in fact, I don't care. There could be 100 numbers after this 9. Just take the rest of them and put it on the end, which here, I mean, it's only 9. There. That is the merge algorithm. Very easy. Look at the two numbers. Which one's smaller? Take it, then go to the next number. Keep doing it until you're done. And what do I have here? I have a list of I have one list now that's sorted. It's bigger than the other two. In fact, it's twice as big as they were. But now I've done that merge. How much work was that merge? In terms of n, where the list is size, each of those lists were size n. How many steps were there? Two n minus 1, you're thinking too hard. I mean, yes, but you're getting too precise. Remember, we're lazy. We'd be like, well, it's 2 times n, right? But do we care about coefficients? No. So it's like linear. It's n. Because we think about how this grows. If n was 7, well, it's going to take like 14 steps. If n is 100, it's going to be like 200 steps. If n is n, well, it'll be 2 times n. But again, we don't care about those coefficients because it grows linearly. So the merge algorithm takes n steps. It's linear. So if I start with a big list and I keep having it and having it and having it and halving it and halving it, all the way down until I end up with n lists of size 1, all those lists are sorted. All the lists of size 1 are sorted, right? So that I can run that merge algorithm on those sorted lists. So again, at each level, a merge takes linear time. But how many levels are there? Well, we saw where we were doing that halving and halving and halving and halving and halving. We get down to, there's log n levels. Yep. So we looked at this before, right? If I do something like this, now to move away from sorting. I can do this, right? Because what is A? In this example code, what is A? It's a reference to a list. And then what did I append to A on line 2? The reference to the list. Which is weird, right? The list contains a reference to itself. It's kind of funny, right? But it totally works. What is A at 0? Good. What's A at 1? What's A at 2? A at 3. A at 4. What was A at 4? Well, it was the whole list. Okay, so what's A at 4 at 0? A at 4 at 1. A at 4 at 4.
What number is bigger than 4?
Nope. But I can do this. I keep indexing it, like I keep making it reference itself. This is absurd. This is ridiculous. Don't do this. But if you're a good computer scientist, if I teach you rules, what you want to do is, within these rules, what can I do? I'm not breaking any rules. We are not breaking any rules. We just appended a reference to a list in that list. It just so happens that it's a reference to itself. It's in this, it's where we get things that reference themselves. Self-reference is a weird thing. Now, I talked about this in a lab earlier this semester, so some of you here will have heard this before. And going all the way back to the beginning of the semester, this statement is false is kind of problematic. The statement is referencing itself. It's making a statement about itself. But we are in a funny situation if we say this statement is false. Because if I start by believing that statement, let's assume that statement is true. If it's true, it tells me it's false. But that can't be right. Because if it's true and it tells me it's false, then I need to believe that it's false. But it was just true. This self-reference can create some really weird things logically. I mean, if I tell you this statement is false, you think, that's a funny paradox. You know, our brains can deal with that. But in terms of like a mathematical statement, this is a problematic mathematical statement. This is a conundrum. We're in a paradox. This statement is false, is incomprehensible. It's a non-computable sentence because if it's false, if it's true, I believe if it's true, then it's false. But if it's false, then it's true. What? It can't be both. So we're in this funny paradox. It's the same one with Pinocchio saying, my nose will grow now. Pinocchio says his nose will grow now. Well, his nose only grows when he lies. That means he's lying. So if he's telling me right now his nose is going to grow, that means he's lying. But then that would mean he's telling the truth, and therefore his nose shouldn't grow. But he told me that it's going to grow. What? Do we see the problem here as well? Pinocchio saying, my nose will grow. His nose only grows if he's lying. But if his nose grows, that means he was telling the truth. Which means he wouldn't have been lying, which means his nose couldn't have grown. These are like non-computable ideas. This is where we run into problems in our universe. You know, we like to think of math being this great thing that can help us answer all these different questions. You want to know probably the most important critical mathematical discovery of the last 100 years is there's a proof that says we can't prove everything with math. There is a proof that says, like, yeah, give up.
Yeah.
Which is kind of crazy. You go back 100 years ago, like mathematicians, your average mathematician wouldn't think that. Your average mathematician would be like, no, we're just working on it. We're getting there. Until someone came along and proved that you can't. There's things that are you can't prove. It might be true, but you can't prove it. And we don't know what is and is not provable. We are in quite a mystery. We're in quite a predicament. All right, I'll see you Friday.